Section 1.52, the fundamental theorem of calculus. Now let f be a continuous function on AB, closed interval. It's very important that it's closed. Define big F of x equal to the integral from a to x of some small of the f we just mentioned, ft dt. Notice that we do not want to use the same variables here because that will get way too confusing. So it's you make sure you use different variables to indicate what we're doing here. So whereas x of course must be between a and b because that's where little f is defined. So if this situation is true, then big F's derivative of x is exactly the same as small f of x. In other words, derivatives and integrals are somewhat inverse functions. Now, the proof of the fundamental theorem of calculus relies heavily on the mean value theorem of integrals. And we will prove it like this. First, we'll go by the original definition of derivative. This is what we're driving at. So this is what we start. F of x plus delta x, okay, minus f of x. This is part of the definition of the derivative. But first, we'll figure out what that is. What is it? Well, looking at the definition of big F, this means it goes from a to integrate from area from a to x plus delta x, subtracted the part that goes from a to x. So what you have left is then x from x to x plus delta x. That's the only part that's left. Okay, so then the inside is ft dt. All right, and the next thing we're going to do is quote the mean value theorem. The mean value theorem says of integrals says that this thing, the integral of x to x plus delta x f t dt is equal to f b minus a, okay, the top minus the bottom, which is just delta x, times f times something inside. There's a value inside that's such that this relationship exists. And that's the mean value theorem, where big X has to be between these numbers. So it's bigger than or equal to small x and x plus delta x. All right. So then we combine these two equations and we get f times x plus delta x minus f times x divided by, we'll divide this thing out, delta x, okay, substitute that and that, which is going to be equal to f of big X. And again, big X is something in between x and x plus delta x. That's very, very important. It's limited only to a value inside there. All right, now at this point, you notice the reason we write it this way is to approximate this. That limit as delta x go to 0 is exactly f prime. That's what we're driving at. So for this proof, let's hold x fixed because we're considering only one x at a time. Okay, so x is fixed. Let delta x go to 0. What happens then? Then this becomes the f prime of x. Okay, and then more importantly, this big X will go to small x because big X is limited between them. As the delta goes to 0, big X is squeezed into small x, which means, so what we get here is this thing, the left side becomes f prime of x equal to the right side is f of, remember the big X becomes small x, so that equal to f of x. And that is well, as big X goes to small f of x, then f of big X becomes f of small x. Why? Because f is continuous. That's where the continuity kicks in. It also kicked in when we did the mean value theorem, which requires it as well. But in any case, because f is continuous, as big X goes to small x, the small f x, then f of big X also goes to f of small x. And that actually concludes our proof. See, a quick and easy proof. Now, the consequence of the fundamental value of calculus is, of course, let's say you have a function f that's continuous on a closed interval AB. As same requirement as here, so that our fundamental theorem holds. Then, if you have the equation, to solve the equation dy by dx equal to f of x somehow, to solve this equation, the solution to this equation is, by the fundamental theorem, the integral from some constant to x f t dt. And it doesn't matter which constant, the derivative will come out the same. And as long as it's the same one here, of course. We will pick the same one here, and plus a constant c, because the derivative is unique up to a constant, as we have mentioned earlier. And that concludes our proof.